The following Zoom session is being recorded and will appear later today on my YouTube channel, Math with Mayo. Therefore, when you participate in the Zoom meeting, if you do not wish for your picture or your name to be made public, please leave the video off and use an alias name. If you have questions during the meeting but do not wish to speak, email me at bmail@ybcc.edu and I'll respond as soon as I can. All right, so today, eventually, we're going to go on to section 9.2. But before we do that, we have a couple of questions from section 9.1. So this is from 9.1, and this is number 24. It says, use a calculator to find each function value, round to the nearest 10,000th. And our function is g of x equals the square root of 7 minus 4x. All right, first of all, part A, we are to find g of negative pi. And then part B, we are to find g of 0.5. So let's take the negative pi first. G of negative pi would be the square root of 7 minus 4 times negative pi, which would be the square root of 7 plus 4 pi, because negative 4 or minus 4 times negative pi, negative times negative is positive. All right. So on your calculator, let me see here. On the left-hand column, the fourth button down, at least on my calculator, I have the pi symbol. Karina, were you able to find the pi symbol on your calculator?
I've been using an online calculator, and I think when you were saying plus pi is where I messed up. But
oh, okay,
yes, I was able to find it.
But you were able to find a pi button.
Yes.
Okay, all right. So going on my calculator, I'm going to go second square root. So that now I've got this showing up. Then I'm going to put in 7 plus 4 pi. Close it up with a right-hand parentheses and push equals. And I get 4.423389042. It said to the nearest 10,000th. This is the 10th, 100th, 1000th, 10,000th. The 8 would round up. So 4.4234 would be the correct answer for part A. All right with that? Yeah, I could see why if you had a minus 4 pi, that would give you a negative value inside, which is why you would put undefined. Yeah, okay.
Yes. All right, thank you.
Yeah, and then g of 0.5 would be the square root of 7 minus 4 times 0.5, which is the square root of 7 minus 4 times 0.5 is 2. So we've got the square root of 5. And the square root of 5 is 2.23606. And the 0 would be in the 10,000th. The 6 would round up to 2.2361. All righty. And then we have question number 32, also from 9.1. Take a look at that. Okay. It says, simplify the radical expression, assume the variable is unrestricted. Okay, the fifth root of negative the quantity 32x to the fifth. All right. Since we're taking an odd root, there's no restrictions. We can get a negative answer. All right. Now, negative the quantity 32x to the fifth would be the same thing as negative 32x to the fifth. The fifth root of negative 32, well, would be negative 2, and the fifth root of x to the fifth would be x. And I see what the problem was. You put absolute value bars on it, but you wouldn't use them here because you're taking an odd root.
Okay.
If it was an even root, then yes, you'd need them. But for an odd root, you can get a positive or a negative answer. Right.
Okay.
We good to go on that?
Yes.
Okay, well, then let's go on to section 9.2. And hang on here. Let's see. What we're going to look at today is how radical notation and exponential notation relate to each other. Let's say I have the cube root of 2 squared. Okay. So this is radical notation, where the power inside is a 2 or a second power. The index is a 3, implying a cube root. To write this same expression in exponential notation, we would have 2 raised to the 2/3 power. So the index on the radical becomes the denominator of the exponent. And the power inside becomes the numerator of the exponent outside. So the cube root of 2 squared would be the same thing as 2 to the 2/3 power. So we've got the power on the top and the root on the bottom. So we have an exponent that is a fraction. So for instance, the square root of 4 would be written as 4 to the 1/2 power. Now, where did I get the 1/2 power? Well, 4 is an implied 4 to the 1 power. And when there's no index written, it's an implied 2. So the square root of 4 is equal to 4 to the 1/2 power. Excuse me, boy. Are you okay with that? Let's take a look at another example. The cube root of 8 would be 8 to the 1/3 power. Let's find both of these on our calculator. So the first one, we would put in a 3, then we would access the x root by hitting the second button, and then the, let's see, what do we do here? We put in a 3, then a second button, and then the little caret key. So we get the 3 and then the x root of, okay? Then you put in an 8 and push enter, and you should get 2. Doing it this new way, you'd put 8 and then the little caret parentheses, 1 divided by 3, close parentheses. So 8, little caret parentheses, 1 divided by 3, close parentheses, and you also get 2. Now, a common mistake that students make is they forget the parentheses and they write this. The way the calculator interprets that is that's 8 to the 1 power divided by 3. So you end up getting 2.6 repeating. You've got to tell the calculator that the entire fraction 1/3 is the exponent, so you have to group it as such. All right, any questions about that? Okay, so let's take a look at some examples here. It says evaluate each expression. 125 to the 1/3 power. So this is basically the same thing as the cube root of 125. Well, what number times itself is 125? Antonio, can you turn off your microphone, please? We're getting all the paper shuffling coming through. Antonia?
Sorry, my audio,
There you go. Thank you. Okay. All right. What is this? What's the cube root of 125?
5.
5, right? Because 5 times 5 is 120, or 5 times 5 is 25 times 5 is 125. So 125 to the 1/3 power is 5. On your calculator, you could put in this, and you should also get 5. All right. Any questions there?
No.
Okay, how about this one? 81 to the 1/4 power. So that's the same thing as the 4th root of 81. Well, let's see, what times itself times itself times itself is 81? That would be 3. So 81 to the 1/4 power is 3. Okay. Any questions there?
Nope.
All right. How about this one? 1/4 to the 1/2 power. Well, that's equal to what? The square root of 1/4, which is 1/2. We okay with that?
Yes.
All right. Now, this next bunch of problems, it says, simplify each expression. Assume that the variable can be any real number. In the previous section, they said, assume the variable is unrestricted. Same idea. And use absolute value symbols when necessary. All right. 4x to the 4th to the 1/2 power. Before we do this problem, let's go back to section 5.2 and review some of the exponent rules. The one we would need to review for this is called the power rule. It says that a power raised to a power, you multiply the exponents. Okay. Actually, wait a minute. That's not the one I wanted. We're going to use that in a minute. The first one I want is this one that says the power of a product. If you have a product raised to a power, you attach the outside power to each factor inside. So the product xy raised to the n power becomes x to the n, y to the n. Let's say, for instance, we had 3x, the quantity squared, we'd have 3 squared x squared or 9x squared. Okay, so that's like back in chapter 5. Now let's apply that to this problem. We have a product raised to a power. So we're going to attach that outside power to each factor inside. Okay. Now, this is where I'm going to use that rule that I introduced a minute ago, and that's the power rule. It says this: if we have a power raised to a power, you multiply the exponent. So let's say I have x squared to the 8th power, that would be x to the 16th power. Okay, I'm going to use that right here. 4 to the 1/2 power, that would be the square root of 4, which is 2. And then x to the 4th to the 1/2 power would be x to the 4 times a half, which is 2. So we get 2x squared. Now the question is, do I need absolute value bars on this? And the answer is no, because since x is being squared, even if x was negative, negative quantity squared would be positive. So my final answer is 2x squared. But I used this rule and this rule from before. Okay, a product raised to a power, attach the outside power to each factor. A power raised to a power, multiply the exponents. All right. Any questions there? How about this one? X cubed to the 1/3 power. We have a power raised to a power, so you'd multiply the exponents. 3 times 1/3 is 3/3, which is 1. So the answer is just x. Now, do I need absolute value bars? No, I'm taking an odd root, so I could get a negative answer. So the answer is just x. Doing all right? How about,
Yes.
okay, how about this one? X squared to the 1/2 power. So a power raised to a power, you would multiply the exponents. 2 times 1/2 would be 2 halves, which is 1. So we get X. However, we're taking an even root, and we're told that the variable can be any real number. So in this case, I actually need absolute value bars on the answer. All right. Good to go on? Okay. -64 p to the 8th power to the 1/2 power. I have a product raised to a power. So this would be -64 to the 1/2 power times p to the 8th to the 1/2 power. -64 to the 1/2 power, that's the square root of -64. P to the 8th to the 1/2 power is p to the 8 halves or p to the 4th power. But what is the square root of -64? Not real. So the answer is not real because we can't take an even root of a negative number. All right, that was one of the things from yesterday, one of the big things. Now, let's take a look at this example. -64 t to the 9th power all to the 1/3 power. So this is -64 to the 1/3 power, t to the 9th to the 1/3 power, which is -64 to the 1/3 power, t to the 9 times 1/3 would be 9/3 or 3. Can I take the cube root of a negative number? Yes, I can. So we get -4 t cubed. -4 times -4 is +16 times -4 is -64. So the cube root of -64 is -4 because -4 times -4 times -4 is -64. All right. Well, let's go on. Let's see here. 27 to the 2/3 power. Now, when you have a base, a number, a variable, a quantity, raised to a fractional exponent like we have here, we can pull apart the power and the root as long as they are both real. So for instance, I could think of this as 27 squared to the 1/3 power, or 27 to the 1/3 power squared. In other words, I can take the power first and then the root, or I can take the root first and then the power, as long as both of those original quantities are real. So we're not taking an even root, excuse me, of a negative number. Now, since I can do these either way, which one's easier? Well, let's say I want to do it in my head. 27 squared, no idea. I could calculate it out, but probably not in my head. I'd get this humongous answer, and then I'd have to take the cube root of that. But if I do the bottom one, 27 to the 1/3 power, the cube root of 27 is 3, and then 3 squared is 9. So given a choice, I would go the bottom route. Now, I could do these on my calculator, and it wouldn't matter either way. I could go 27 raised to the 2 divided by 3 power, and I should get 9. But I'm just saying by hand, you could do the root first, and it would be easier than doing the power first. Okay with that? Well, we'll find out, I guess. All right. How about this one? Negative 100 to the 3/2 power. Now, this is negative 100 cubed. No, it's not. Hang on. That exponent is not on the negative side. If it was written this way, then the negative would be included, but it's not. So basically, this is the same thing as like negative 1 times 100 to the 3/2 power. This negative sign is not part of the base because it would have to be grouped if it was. Okay. So then this is what? Negative 1 times. Let's do the root and then the exponent. Okay. What's the square root of 100? That's 10. 10 cubed would be 1,000. So we get negative 1,000 as our final answer. Now, contrast that with this problem. This would be not real because now your base includes a negative and you can't take an even root of a negative number. Okay. All right, with that, that goes back a ways. Okay. How about this? It says, simplify each expression. All variables represent positive real numbers. So we don't have to worry about absolute value bars for this particular problem. So I have a product raised to an outside power. So I will attach that outside power to each factor inside. Okay. 27 to the 2/3 power. I could write that as 27 to the 1/3 power squared. A to the 3rd to the 2/3 power is a to the 6/3 or a squared. B to the 3rd to the 2/3 power is b to the 3 times 2/3 or 6/3 or 2. The cube root of 27 is 3. 3 squared is 9. So there's my final answer. Do you want me to go through any part of that slower or again anyway or what?
Could you go through it again, please?
Absolutely. Not
Thank
a problem at all. All right, first of all, we have a product raised to an outside power. So using, let's see here. Where was that rule? This rule, product raised to an outside power, we attach that outside power to each factor inside. So that's where I get 27 to the 2/3 power, a cubed to the 2/3 power, b cubed to the 2/3 power. So far, so good?
Yes.
All right. Now I'm going to take the 27 to the 2/3 power and I'm going to split it apart and do the root and then the exponent. Okay.
Yes.
27 to the 1/3 power, the cube root of 27 is 3. That's squared, so that's going to give me 9. Let's take a look at the second expression. A cubed to the 2/3 power, a power raised to a power, you multiply the exponents. 3 times 2/3 would be 6/3 or 2, so we get a squared. Okay with that?
Yes.
And then b cubed to the 2/3 power is going to be the same thing. So we get 9a squared b squared as the final answer. All right with that?
Yes.
Okey doke. Let's see here. One 16th x to the 8th y to the 4th all to the 3/4 power. If I have a product, let's see here, raised to a power, as before, I attach the exponent to each factor. If I have a quotient raised to a power, I attach it to the numerator and the denominator. If I have a combination of a product and a quotient, I attach it to all the factors in the numerator and all the factors in the denominator. So this is sort of a combination of these two rules. And that again goes back to section 5.2 and 5.1. Are you okay with that?
Yes.
Okay, so now we're going to take 1 to the 3/4 power over 16 to the 3/4 power, x to the 8th to the 3/4 power, y to the 4th to the 3/4 power. So I attach that outside exponent to each factor in the numerator and in the denominator. So to the 1 to the 16, x to the 8th, y to the 4th. Are we good so far?
Yes.
All right, let's take this one piece at a time. Let's take a look at 1 to the 3/4 power. 1 to the 3/4 power. Well, we could do 1 cubed to the 1/4 power. What's 1 cubed? What's 1 times 1 times 1?
1.
What's 1 to the 1/4 power?
1.
1. Okay, so this is 1. All right. Now let's deal with this piece. 16 to the 3/4 power. Well, I could do the 1/4 power and then cube it. Remember, I can do the index first, or the root. What's the 4th root of 16?
2.
So this is 2 cubed, right? Which is 8. Let's make this a little shorter here. Okay. Still with me?
Yes.
All right. Let's take a look at this piece. A power raised to a power. We'd multiply the exponents. 8 times 3/4 would be 24/4 or 6. You could reduce the 8 and the 4 to 2 over 1, and you'd have 2 times 3 is 6. Over 1 is still 6. Okay. All right with that?
Yes.
Okay. And then let's take a look at this one. So y to the 4th to the 3/4 would be y to the 12/4 or y to the 3rd. And there's your final answer. Or you could write it, what, x to the 6th, y cubed all over 8, like that. All righty. We good to go on?
I am.
Tonya, we good? I guess so. Okay. All right. This says change each radical to an exponential expression. So we're going to go back and forth between the two forms. The 7th root of 7p squared q would be the quantity 7p squared q to the 1/7 power. The index becomes the denominator of the exponent. The square root of x squared plus y squared becomes x squared plus y squared all to the 1/2 power. Questions on those examples? All right. Going the other direction, change each exponential expression to a radical. 7a squared b squared to the 1/3 power becomes the cube root of 7a squared b squared. Again, the denominator of the exponent becomes the index. Or x cubed plus y cubed all to the 1/3 power becomes the cube root of x cubed plus y cubed. Good to go on?
Yes.
All right.
Good.
Oh, question?
No.
Okay, all right. Let's review another rule from back in chapter 5, and that is a base raised to a negative exponent is 1 over the base to a positive exponent. Likewise, if you have 1 over a base to a negative exponent, that's the base to a positive exponent. So go across the line, change the sign of the exponent. Let's say you've got something like this. You could flip them both, and they both end up with positive exponents. Or let's say you had b over c to the negative 1/2 power. That would be c over, that would be c over b to the positive 1/2 power. Because you're taking the reciprocal, so you change the sign of the exponent. Okay, so again, that's a review rule from back in Math 85, back in section 5.2. Now, how's that going to work here? Let's say I've got 4 to the negative 1/2 power. You can't have a negative index. You can't have like the negative 2, like the negative 2 root of 4. Can't do that, okay? But this could be 1 over 4 to the positive 1/2 power, which would be 1 over 2 or 1/2. 8 to the negative 1/3 power would be 1 over 8 to the positive 3rd power, 1/3 power, which would be, again, 1/2 because the cube root of 8 is 2. Okay with that?
Yes.
All right. How about this one? 25 over 49, all to the negative 3/2 power. So that would become 49 over 25, all to the positive 3/2 power. And that would be 49 to the 3/2 power over 25 to the 3/2 power. I could do the root first and then the power in both the numerator and the denominator. So I'm pulling apart the 3/2, making it 1/2 times 3. But the square root, or the 1/2 power of 49, is 7. 7 cubed is, I believe it's 243. Let's see, 7 times, helps if you turn it on first. 7 times 7 times 7 is 343. I was only off by 100. And then the square root of 25 is 5. 5 cubed is 125. Any questions about that? Okay. Let's go back and review another rule that says multiplying two powers with the same base, you add the exponent. So like x cubed times x to the fourth is x to the seventh. Y to the sixth times y to the 10th is y to the 16th. Now, don't confuse that rule with this one that says when you're raising a power to a power, you multiply, because here you get this, and here you get that. So very different, okay? When you have a power raised to a power, you multiply the exponents. When you're multiplying two powers with the same base, you add the exponents. So let's say I have 9 to the 3/7 power times 9 to the 2/7 power. That would be 9 to the 3/7 plus 2/7 power, which is 9 to the 5/7 power. Multiplying two powers with the same base, add the exponents. If I have 4 to the 2/5 power times 4 to the 2/5 power, that's 4 to the 2/5 plus 2/5 power, which is 4 to the 4/5 power. What if I had 4 to the 2/5 power times 4 to the 3/5 power? That would be 4 to the 2/5 plus 3/5 power, which is 4 to the 5/5 power, which is 4 to the 1 power, which is just 4. So that would equal 4. We're good to go on?
Yes.
Yeah.
Okay. I guess I'll just keep going, and if I need to stop, you yell stop and I will. 5 to the 1/3 power times 5 to the negative 5/3 power would be 5 to the 1/3 plus negative 5/3, which is 5 to the negative 4. 5 to the negative 4/3 power, which is 1/5 to the positive 4/3 power. Again, I want to write answers without negative exponents. All right. B to the 3/5 power times b to the 2/5 power, all to the 8th power. Order of operations, inside grouping symbols first. Well, inside I'd have b to the 5/5, which is b to the 1, or just b, and then to the 8th power outside. So final answer, b to the 8th power. Here, okay. All right with that?
Yes.
Okay. Let's see, how are we doing for time? Another rule, let's review. Let's say you've got a power divided by a power where the base is the same. So you're dividing two powers with the same base. Here, you have the base to the top exponent minus the bottom exponent. So x to the 5th over x squared would be x to the 2, but 5 minus 2, or x cubed. So you'd take top exponent minus bottom exponent. Okay. Again, that's a review of rules back in chapter 5. So let's say I've got this 2 to the 5/6 times 2 to the 1/3 all over 2 to the 1/2. All right. So in the numerator, I've got 2 raised to the 5/6 plus 1/3 power. But to add 5/6 and 1/3, I need a common denominator, which would be 6. So I've got to multiply 1/3 by 2 over 2, which gives me 2/6. So then I've got 7/6. So now I've got 2 to the 7/6 power over the 2 to the 1/2 power. Okay. So we combine these two by adding the exponents, and to do that, we needed a common denominator. Now, next, I'm going to divide these two powers, so I've got to subtract. So I'm going to get 2 to the 7/6 minus 1/2 power. But 7/6 minus 1/2, we take the 1/2 and multiply it by 3/3. So minus 1/2 becomes minus 3/6. 7/6 minus 3/6 is 4/6, which reduces down to 2/3. So I end up with 2 to the 2/3 power, because all of that became that. Isn't that a fun one? Here, that's your final answer. Good review there of adding and subtracting fractions, common denominators and whatnot. Welcome back to Math 50, which I guess is Math 80 now. All right. We good to go on? Okay.
Yes.
Here we go. We're going to distribute now. Again, assume all variables represent positive real numbers. Y to the 2/5 power times the quantity y to the negative 2/5 plus y to the 3/5 power. Okay. I can't combine the two things inside parentheses. They're not like terms. So I'm going to distribute. I'm going to get y to the 2/5 times y to the negative 2/5 plus y to the 2/5 times y to the 3/5. Distributing. Let's deal with this. We're multiplying two powers with the same base. So we're going to add the exponents. We're going to get y to the 2/5 plus negative 2/5, which is y to the 0 power. Do you remember what something other than 0 raised to the 0 power is?
1.
Good job. So that's 1. Here, multiplying two powers with the same base, we're going to add the exponents. We're going to get y to the 2/5 plus 3/5, which would be y to the 5/5, which would be y to the 1, or just y. So final answer, 1 plus y. Any questions there? You're definitely getting your money's worth today.
No.
All right. The directions say use rational exponents to simplify each radical. All variables represent positive real numbers. So what we're going to do at this point, we're going to take this radical expression, we're going to rewrite it as an exponential expression, and then simplify it, and then go back to writing it as a radical expression. Eventually, we'll get to where you can skip that step. You can just simplify it as it is. But for right now, so this is going to be 7 to the 3/6 power, okay, which is 7 to the 1/2 power, which is the square root of 7. Okay with that?
Yes.
All right. The 12th root of 13 to the 4th power. So that's 13 to the 4/12 power, which is 13 to the 1/3 power, which is the cube root of 13. the sixth root of x squared y squared. That would be x squared y squared to the 1/6 power, which is y squared to the 1/6 power, or excuse me, x squared to the 1/6 power, y squared to the 1/6 power, which is x to the 2/6 y to the 2/6, which is x to the 1/3 y to the 1/3, which is xy to the 1/3, which is the cube root of xy. Usually about now, somebody says, can't you just take this divided by that? That's exactly what we're doing in exponential form. But as I say, as when we get comfortable with it, we can do it just in radical form. But for now, they're having you convert it into exponential form, simplify it, and then convert it back. Okay. All right, here comes a fun one. You say fun for whom? The fourth root of the square root of x. So that would be the square root of x to the 1/4 power, because this whole thing becomes that. But the square root of x would be x to the 1/2 power. So x to the 1/2 power to the 1/4 power. But that would be, oh, a power raised to a power, multiply the exponents. 1/2 times 1/4 is 1/8. And that would be the 8th root of x. So we get from here to here. And what did I end up doing? Multiplying the indices, however you say that. But again, they're saying to go this route for now. Well, I think I've tortured you enough for today. So we'll call it quits. I'll be back at 1:15 this afternoon with an office hour. Or if you have questions and you can't make it, email me. Otherwise, I will see you all tomorrow. We'll stop the recording.